Thank you, Patrick. It's a great honor and pleasure to be able to appear in this very interesting and worthwhile workshop. Most of us who work in the peridynamics area have, at one time or another, been challenged to explain the role of non-locality. Non-local continuum mechanics is not something that people are usually familiar with from their formal education. So people ask, what is the horizon? How do you choose the horizon? How do you choose the micromodulus? What does it all mean? So I've been thinking a lot about those questions, and this talk is kind of what I came up with. One observation that I've made is that non-locality is not quite as foreign a concept as most people in continuum mechanics think that it is, and I'll explain what I mean by that. I will explain that peridynamics is distinguished from most other sort of alternative theories of continuum mechanics in that it goes all in on non-locality. All interactions are non-local, and partial derivatives in space are not used at all. And then I will talk about whether non-locality can be deduced from other theoretical considerations or from experimental data. I think that in general, maybe the continuum mechanics community tends to ask a little too much of the Cauchy continuum mechanics theory, which is local and relies on partial differential equations. So we're always putting more stuff on the Cauchy theory, fractures, phase transformations, non-local, nanoscale interactions and all kinds of other things. So the general philosophy of aerodynamics is that instead of adding more bicycles onto the pickup truck, we're going to try to build a bigger pickup truck that it more easily encompasses problems that arise in modern technology. The general purpose of peridynamics is to treat deformations with evolving discontinuities, especially cracks, according to the same basic field equations as points where the deformation is continuous. Another objective is to include long-range forces like van der Waals forces or other forces that occur at the nanoscale. And also to fit all of this into a thermodynamic framework that's fully consistent with the mechanical theory. So most people say, they sort of get that objective, that it would be sort of cool to have a continuum mechanics theory that allows the field equations to be applied directly on evolving discontinuities. But then they say, well, that's okay, but what about this? What's up with this non-locality thing? I don't get that at all. Where does that come from? And I claim that most people are more accustomed to using non-local concepts in continuum mechanics than they may realize. For example, whenever we discretize the Cauchy differential equations of continuum mechanics, we end up with a non-local mathematical system. And the most obvious case of that is in a finite element or finite difference code, node I interacts directly with node J through some equation, but there is a finite distance between I and j. And my view is that that's a form of non-locality because it's inserting a length scale into a problem just by virtue of the mathematical formulation. And someone could answer to that, yeah, well, that doesn't count as non-locality because as you refine the grid, this distance approaches zero, so you end up with partial differential equations that you're trying to solve. And that's true, but that's also true of peridynamics because, as I'll discuss in a few minutes, as you reduce the non-local length scale, the horizon in peridynamics, to zero, you end up with basically the partial differential equations of the local theory. So what is the motivation for non-locality? The standard theory of continuum mechanics sort of gets itself into trouble when applied to a number of problems of technological interest. For example, if you have a stress-strain relation which is monotonic in the 1D sense, then everything's okay. You get the expected smoothness of elliptic PDEs in equilibrium. But if you have a material model that's non-monotonic, it goes up like this purple curve, and then goes down, and then goes up again. Oops. There are values of stress corresponding to multiple values of strain, which can coexist with each other across phase boundaries. So if you have, if you're solving a boundary value problem with that type of material, and suddenly a phase boundary appears, then all of a sudden you have a problem with this differential equation because it no longer applies because you can't evaluate the partial derivatives, at least not in the strong form of the equation that are required. So this type of thing is even more severe with this a material like this red one, which will try to form cracks. So that's what I mean by the PDEs getting themselves into trouble. They evolve into results that turn out to be not so good with respect to applicability of the original differential equation. So the way people fix this is, well, let me show you an example of a very common situation in the impact and penetration mechanics communities, and that is a dynamic shock wave. So in this graph, there is a shock wave moving to the right. The ideal solution corresponding to the weak form of the PDEs is this jump discontinuity in stress and velocity. But that turns out to be difficult to implement in finite difference or finite element codes because you get all kinds of unwanted oscillations and noise and instabilities. So the way everybody mitigates that problem is to use artificial viscosity, which was introduced by von Neumann almost 70 years ago. And that consists in modifying the PDE to include this term that involves the derivatives of the velocity. And the effect of that is where there is a jump in velocity, this term gets big, so it introduces a stress, in effect, that spreads out the shock wave into this type of curve. And after that, everything's fine. you can apply the difference formulas or finite element formulas without worrying about these, this non-physical noise that would otherwise occur. It also happens to dissipate exactly the right amount of energy to be thermodynamically consistent with the actual thermodynamic path in a shock wave. But my point here is that artificial viscosity, which everybody uses, is a non-local term. It introduces a length scale, which is artificially chosen to be about 5 or 6 element widths. Therefore, what you end up with is a non-local approach to solving a mathematical system that was nominally local to start with. So in contrast, Aerodynamics goes all in on non-locality. Every aspect of it is non-local. So one way of classifying different theories is according to whether they're more or less non-local. So the Cauchy continuum mechanics formulation is completely local. There's no length scale. There are quite a few approaches that augment the Cauchy local equations with various non-local terms like the one I just described. And I would consider phase field to fall into this category because it builds on the local mechanics equations by introducing a new field which evolves according to a non-local equation. It explicitly contains a length scale, as I understand it. So in contrast, Aerodynamics doesn't use the differential operators in space at all. What the Aerodynamic equations look like are basically, this is the equilibrium equation. So instead of the divergence of the stress tensor field, we have this term that sums up force interactions across bonds from x to q of finite length. There is a cutoff distance for these interactions called the horizon, delta, and everything within the distance delta from x is called the family of x. F is provided by a material model which looks at the deformation of the family and comes up with values of the bond force densities which appear in this integral. The formalism for dealing with these non-local interactions uses mathematical objects called states. And a state is simply a mapping from bonds in a family, like this one, from x to q, onto some other quantity. For example, the deformation state, y, maps bonds onto their deformed image under some given deformation. States are non-local analogs of second-order tensors because they map vectors into vectors, but they're more general because a second-order tensor always maps a sphere into an ellipsoid, whereas a state maps a sphere into a much more general state, a much more general image which can contain discontinuities like cracks. So without going into too too many details of the theory, this compares the structure of the peridynamic theory with the standard theory. And you're not too far off by viewing the peridynamic theory as pretty much the same as the standard theory, but it uses these non-local operators. For example, vector-valued states, which I just talked about, rather than second-order tensors. But the mathematical structure is really pretty similar. We have kinematics. The deformation state basically takes the place of the deformation gradient tensor in the standard theory. You have momentum balance, angular momentum balance, material models, which in peridynamics are state-valued functions of a state rather than tensor-valued functions of a tensor. There are also statements of the first and second laws of thermodynamics, which are fully consistent with the mechanical theory. Damage is implemented by usually by breaking bonds, meaning that according to some bond breakage criterion, when a bond breaks, it stays broken, and after that, it no longer sustains any tensile bond force density. The main feature that all of this buys you, and the main feature of peridynamics that people use on an everyday basis, is autonomous crack growth, meaning that bonds do whatever they want. They break according to whatever conditions they find themselves in relative to the damage criterion. But in practice, they organize these bond breakages on two-dimensional type surfaces in a three-dimensional simulation. And we interpret those two-dimensional surfaces as cracks. So nobody's telling these cracks what to do. They just do whatever they want. There's no supplemental kinetic relation for crack growth. And that's kind of the essence of aerodynamics. Many studies have been done looking at the capabilities of aerodynamics in simulating fracture problems of various kinds. And Patrick has done the community a great service by compiling many of these into a review article that appeared in the Journal of Aerodynamics and Non-Local Modeling. Many studies have shown that the peridynamic equations converge to the local PDEs, provided that the deformation is sufficiently smooth. And remarkably, Rob Clifton and his team have proved that if you have a non-monotonic material model in peridynamics, like this up-down-up material that I talked about earlier, and argued that that material gets the local PDEs into trouble, the peridynamic analog of that material has a remarkable property. In the limit of small horizon, it creates cracks, Griffith cracks, that are discontinuous. They contain a finite jump in displacement, and remarkably, as they grow, they consume a definite amount of energy per unit surface area. So they're essentially Griffith cracks. This is a typical application of aerodynamics. This is the growth of a macro scale fracture that grows by joining up pre-existing defects. This is an illustration of fragmentation of a brittle cylinder striking a rigid plate. This is a simulation of microstructure evolution using this up-down-up material model that I talked about a minute ago. These phase boundaries in peridynamics have a finite width, which is related to the horizon, and they also have a certain amount of energy due to the non-local interactions within this finite thickness of a phase boundary. So that additional energy per unit surface area provides a driving force for these phase boundaries to join up with each other and reduce their total surface area. So that is actually pretty similar to what happens in real life, where actual metal microstructures will very often evolve in such a way as to decrease the surface area of grain boundaries. So now onto the subject of whether non-locality is real in the sense of can it be observed in experiments or can it be derived from other considerations. Well, the most straightforward case is when there really are force interactions that occur over finite distances in the sense of physics. So one illustration of that is this simulation done by Professor Babaru of a nanofiber network. And this is a randomly generated bunch of strings, and each string responds internally according to solid mechanics type forces. But the interaction between the strings is non-local. It occurs over a finite distance and is basically a van der Waals type force. So as you stretch on this nanofiber network, the strings individually tend to remain intact, but they separate from each other because the van der Waals forces are relatively weak. So Florin developed a material model that included both the internal forces and the forces between these fibers with a very reasonable looking result. So that's the most straightforward case. What's a little less straightforward is when there is not an obvious physical field that provides these interactions over finite distances. So to look into whether non-locality can still be valid in such a case, I looked at the problem of an infinite bar with heterogeneities, which are what these blue and red stripes are supposed to represent. And we'll model that with the local theory at the small length scale. So the blue and red stripes have different values of Young's modulus, which is explicitly a given function of position. So here's the material model. Here's the small scale model, which is just the usual local differential equation of continuum mechanics. Then what I'm going to do is apply a smoothing function. It's well known that if you had a huge computer and could simulate every air molecule in this room in detail, you'd end up with a whole bunch of useless information because nobody cares about the position of an individual air molecule, but they might care a lot about some smoothed notion of displacement or velocity or pressure. So smoothing is inherently a fundamentally important tool in going from small scale physics to more useful results at the macro scale. So we'll apply a smoothing function that looks sort of like this, sort of Gaussian looking thing to the displacements in that bar. And we don't know what those are yet. So we'll define the smoothed degrees of freedom by applying this smoothing function over an integral weighted by the density to the small scale displacements. And we'll also define the smoothed density by this equation. So then we'll take the local PDE, multiply it by the smoothing function, and integrate, and we end up with this result, which gives the acceleration of the smooth degrees of freedom, and it involves this integral. Then what? So we just ended up with this, and this sigma prime is just crying out to be integrated by parts. So that's what we do, and we get this. So this is starting to look like a non-local equation of motion, right? Because we're integrating over stress. We're integrating stress over a finite interval in the bar. To drive home this point, it is convenient to define Q such that P is halfway between X and Q. And using that definition, the purpose of which will become evident shortly, we can rewrite this equation in this form. Then we take advantage of the fact that W was assumed to be symmetric and observe that sigma at this point P, that's halfway between X and Q, exerts an equal and opposite force on the degree of freedom at X and at Q. So making all those substitutions, we rewrite this equation in this form. So guess what non-local theory that looks like? That's the peridynamic equation of motion. And this F defined here is the bond force, and it obeys the required anti-symmetry between switching the values of X and Q. So I claim that this sort of motivates the use of non-local mechanics models, even when the underlying physics is local and there are no obvious long-range forces to deal with. So the expression I came up with for the bond force densities is almost peridynamics, and I say almost because it doesn't really contain a material model that will allow us to evaluate sigma and therefore F at any X and Q. So how do we evaluate sigma? Well, if we were ambitious, we could use the convolution theorem and back out the local U from the Fourier transforms of the smoothed displacement and of the smoothing function, and we'd end up with this. But that's too much work, and nobody's going to do that. So But we are free to prescribe a non-local material model that satisfies whatever conditions we choose to prescribe. And one way to define such a non-local material model is to observe that in equilibrium, the local solution has constant stress everywhere. Therefore, we can explicitly evaluate the local displacements, then smooth those displacements and define F to be this material property function, the micromodulus, times the difference in the smooth displacements at x and q. And if you define C this way, then this coughs up the exact value of sigma that you're looking for. So this is one way of defining a non-local material problem in this heterogeneous, smoothed heterogeneous bar problem. If you do that, if you use that material model and graph the micromodulus as a function of position, in the case where the bar is homogeneous but has a relatively soft spot, then the micromodulus in the soft spot is naturally smaller than it is elsewhere. And if you compare the results of doing the equilibrium calculation with the smoothed degrees of freedom using this material model that I just derived, if you compare that, which is the red, which you can't really see because it is right over the blue line is the local solution with the smoothing function applied to it. So this demonstrates that for this problem, the non-local agrees with the local result. But the real reason I'm showing all this is this. If we make the soft spot very, very soft, not quite zero, and repeat that calculation of the micromodulus, which is a function of position, and graph all these micromodulus curves, what you find is that bonds that go from one side of this very, very weak spot to the other have their micromodulus zeroed out. So I claim that that is essentially bond breakage. So conceptually, the point of all this is people say, well, you're arbitrarily assuming bond breakage as your damage model. Where does that come from? So this is one way of looking at where bond breakage comes from. So to summarize so far, what this shows is that when we work with smoothed degrees of freedom, we end up with a non-local linear momentum balance. And in this case, I showed that non-locality can be put in the form of the peridynamic equation of motion. The micromodulus, which is the material model for the smooth degrees of freedom, that can be derived from the small scale material properties, but it always involves the smoothing function. So if you choose a different W, you'd end up with a different micromodulus. An interesting aspect of that example is normally in continuum mechanics, in trying to derive a material model, you would like to be able to prescribe the displacement degrees of freedom everywhere and then evaluate what the forces are. But when we work with the smooth degrees of freedom, it turns out there isn't always a physically realizable small-scale displacement field that generates that. And to see that, you can use the convolution theorem, observe that the Fourier transform of U bar is that of W times that of U. So formally, we should be able to invert the U bar star over W star and come up with a local displacement field. In practice, that doesn't necessarily work too well. For example, if W is a Gaussian function with width LW, and you want to figure out what local displacement field, what small scale displacement field corresponds to a smoothed displacement field, which is also a Gaussian, but with a different length LU. Using this convolution theorem, what we find is that the Fourier transform of the small scale field looks like this. So if this exponent is negative, we're in good shape. It's just this Gaussian. But if it's positive, then we're in trouble because the Fourier transform of the small scale displacements blows up for large wave numbers, and you can't do the inversion of the transform. So what that means is that if your prescribed smooth displacements have more high frequency content than the smoothing function, you can get into trouble because there might not be a small scale displacement field that generates what you assumed were the smooth displacements. Well, so much for that 1D example. This is another example in 2D, which demonstrates a different aspect of using homogenized degrees of freedom. So what this is a 2D composite with alternating layers of stiff and compliant elastic materials. And we're going to look at 1D type deformations. We're going to compress this from the vertical and from the vertical boundaries and see what happens. Our homogenized displacements are just a volume weighted average along vertical lines. Now, if you take two plates located on opposite sides of this composite and just compress the plates together, then lo and behold, you get a linear function of position for the average displacements along vertical lines. So no surprises there. However, suppose you change the problem a little bit, and we still have a rigid plate on the right side, but on the left side we prescribe constant traction along this surface. So individually on these alternating stripes, you have constant force per unit area applied. So should we expect the same result as in the Dirichlet problem? Well, the local theory would say, yes, we should expect the same results if we use an effective modulus found by averaging the elastic modulus among the different constituents. But if you do the simulation in detail using the local theory and you make a plot of the displacements as a function of position, understandably, the soft material deforms more, therefore you get larger displacements there. than in the stiff material. So if you do that detailed 2D calculation and then average the displacements along vertical lines, out here you still get the local result that we looked at in the Dirichlet problem, but near the edge, the smooth displacements have this nonlinear feature. So what's up with that, and how can we represent that in a 1D model of this problem? Well, so I spent some time just playing around with different micromodulus functions in a 1D peridynamic model, which are not a function of position. They're the same everywhere. And trying to optimize the agreement with this detailed but smooth solution that I was just talking about. And a micromodulus like the one shown turns out to reproduce this strange looking feature along the edge where the tractions are applied. So that's an example of where non-local helps you reproduce a homogenized small scale result. So can this be observed experimentally? Sure it can. If somebody wanted to do that experiment and do DIC measurements of the full displacement field, that would be another way to confirm without resorting to this detailed computational model, confirm whether or not non-locality has any role to play in the problem. There was recently a paper also in the journal Aerodynamics and Non-Local Modeling. Patrick was a co-author where they used one of these full field displacement analysis techniques called virtual field method to do exactly that in a not with experimental data but with simulated data. So all that involves statics. What about dynamics? Suppose we take the same composite material and hit it edge on with an impactor and just look at what waves propagate to the right of that impact event. If you do a detailed dynamic simulation, you get a very complex wave structure. And you get the complex wave structure because waves in the stiff material want to travel faster than the waves in the compliant material. But those two things are coupled. So they're not independent of each other. And once again, playing around with different choices of a micromodulus function in 1D, you can get a peridynamic model that reproduces many of the features seen in the homogenized solution to that problem from the detailed 2D calculation. So this is wave dispersion. A local model would give you a square pulse. But the detailed model gives you this spreading out of the waves that I just talked about. Wave dispersion is another opportunity to use experimental data to derive non-local material properties. So what wave dispersion is changes in wave velocity as either the frequency or the wave number are varied. So in materials with a microstructure, dispersion curves for waves that have wavelengths on the order of the microstructure size or less will show features on a dispersion curve. The waves will go either faster or slower depending on the details of the material than longer wavelength waves. In peridynamics, we can derive a dispersion relation, that is, frequency as a function of wave number, directly from the linearized equation of motion by assuming plane wave solutions of this form, resulting in this expression that shows that the frequency is essentially given by the Fourier transform of a micromodulus function. In practice, what these dispersion curves look like is for large wavelengths, that is small wave number, they agree closely with the classical result, which is always a straight line with no dispersion. At higher wave numbers, this curve eventually reaches a maximum and then wiggles for a while. It's doubtful whether waves to the right of this maximum are observable in real experiments, because when you get close to this maximum, the waves start attenuating like crazy, and it's very hard to do any observations. But there are many studies of wave dispersion in peridynamics that have been done. I would call your attention to this one by Dr. Boot, who's here at this conference. And also there was an interesting talk at USN-CCM by a student from India named Mr. McMurray, and he's writing an interesting paper on subjects related to this. So you can reproduce a given dispersion curve just by inverting the Fourier transform of given experimental data from the dispersion curve. The higher the cutoff frequency, the skinnier the micromodulus function after you do this conversion process. So in the limit where this cutoff is very large, this micromodulus starts to look like a delta function, which corresponds to the local limit of the non-local PDEs. I went through this exercise of calibrating a peridynamic micromodulus to measured dispersion data that was published. The material was a boron epoxy fiber reinforced composite. So I evaluated the micromodulus by inverting the Fourier transform of the dispersion curve. Then I took that micromodulus and computed the dispersion curve in the peridynamic model to try to confirm that it agrees with the same data that we started with, and indeed it does. So dispersion data is something that can be measured in the laboratory, and many materials exhibit wave dispersion, not just composites, but concrete wave dispersion can be a big deal in studying wave motion in concrete and many other materials. So in summary, what I have tried to argue is that non-locality, in the simplest case, can arise from actual physical fields that cause force interactions over a finite distance. But also non-locality arises mathematically according to how we choose to model the problem. Specifically, how we do smoothing or how we choose other degrees of freedom that we're using to model the system. So I'll stop there. Thank you.
time for a few questions. Are there any questions? Yeah?
Stupid questions and experiments. You just described how you would get the micromechanical function from the dispersion relation in a material that's softened. What about material that strengthens with the wavelength, as many polymers, for example, do?
Yeah, this dispersion curve can go either where'd it go?
Either soften or harden.
Yeah, so the purple, I think the purple line corresponds to what you're calling hardening, is that right?
Yeah.
So the method still works, even though I've drawn this this to be concave down. It can curve up for a little while, but eventually it will reach a maximum. So the method still works.
Good, it wouldn't change the analytical form of your kernel function and your weighting function, I guess.
Well, it would change the material properties that that you come up with. So for different dispersion curves, and here are two choices, you get different micromodulus functions. Yeah, the details of the micromodulus function would determine the curvature, whether up or down in this regime.
Do we have? Yeah, sir.
So you are talking about these non-local models. What I'm surprised is you are not mentioning molecular dynamics models. And I would like to know if some people have looked at the upscaling of those molecular dynamics models to maybe recover peridynamics. Because there exist a lot of different models for metals and things like that. And basically, the non-local forces, you also have a cutoff distance that usually people introduce, a little bit like the horizon. And it seems to me that if we do some upscaling of these models, we should maybe recover equations similar to peridynamics.
Yeah, coincidentally, you're sitting next to the expert on that, Pablo Salazar.
Yeah, I know him very well.
Yeah, he wrote a paper that demonstrates exactly that, upscaling molecular dynamics into a sort of coarse-grained peridynamic continuum model. So that's definitely possible. There's also a paper by my Sandia colleagues, Mark Sears and Rich LaHoop, where they repeat Irving-Kirkwood type arguments, demonstrating that a statistical mechanics description of an ensemble of a large number of atoms or molecules, all of them in thermal motion, can be coarse-grained into the peridynamic equation motion. So there's that. And that can be done with fewer assumptions than the original Irving-Kirkwood argument that resulted in the local PDEs, which is a very famous result. So yeah, all of that is possible.
Do we have more questions for Stewart? Okay, so let's thank the speaker again. We will have a 30-minute coffee break and we start at 10:30 again.